Okay, so hello everyone. Hope you're doing fine. In the presentation today, I will try to summate the main findings of the research work that I've been doing for the last 2 years, 2.5 years. Particularly, I'll talk to you about a machine learning-based method that addresses the problem of cost overheads in software regression testing, and also be focusing on discussing the importance of handling two types of noise found in the data on the effectiveness of the method. So a quick overview for the next 30 minutes. I'll start by setting some context by briefly describing what regression testing and continuous integration are. And then I'll talk about the overall goal of my research. We'll talk about a bit the research focus, the research methods that I adopted, and the findings from each of the studies that I conducted. And finally, I'll end the presentation by describing some of the practical implications that my research has on different stakeholders in software development companies. And I'll also discuss some open-ended questions that I plan to answer in the future. So what is software regression testing? As you may probably know, software regression testing is a testing practice that we do to evaluate whether a change made in the source code of the system under test has not adversely been affected both functionality and the quality. And we do this by executing different types of test cases, including both functional and quality tests. But then the question is, if we want to execute all different types of test cases, then do we have enough time and resources to execute all of those test cases? And that is essentially why continuous integration exists. As you know, continuous integration promotes for doing continuous integration and testing of code changes several times every day. And this is done with the aid of a platform such as Jenkins, for example, that performs regression testing and maybe do some code analysis check to detect some code smells. And once the continuous integration system finishes the testing phase, it will feed developers with a report specifying the number of test cases that passed and the number of test cases that failed. And based on that report, developers can either go for releasing a new version, or they would just revise and fix issues in the code that were identified during the testing phase. But the challenge in performing regression testing still lies when the number of those code integrations and test cases grow in size, because then we need to have more computer resources, more time to execute these test cases at every integration cycle. And therefore, it becomes very important to try to optimize the orchestration in which those test cases are executed for regression testing. And generally speaking, existing techniques for optimizing regression testing, they fall under three categories: the test suite minimization, the test case selection, and test case prioritization. But all of those techniques share one goal in common, and that is to reduce the size of the regression suite while also maintaining a high rate of fault detection. So on the test suite minimization, we have approaches that seek to identify redundant and obsolete test cases. And by obsolete test cases, we mean test cases that no longer test what they were designed to test in the first place. And this can be due to some modifications made in the program or changes in the specifications. And approaches in the test case selection category, they seek to select a subset of test cases that were presumably impacted by some new changes made in the system under test. And in test case prioritization approaches, they seek to find the optimal permutation or the order of the sequence of test cases in which those should be executed given a predefined criteria. An example of criterion could be the execution time of tests taken. However, not many of the existing approaches for optimizing regression testing have been widely adopted in practice due to a number of limitations, which I'll also touch upon in this presentation. But then the overall goal of my research is to design a test case selection method that can maximize the probability of revealing faults in the system being tested. So given some code changes may be pushed by developers to the development repository, you have a continuous integration server listening to those code changes, creating builds, and performing regression testing. So the goal of this method is to identify test cases that will pass and remove those from the regression suite. We don't want to waste time on executing those tests. And we only care about, including trying to maximize the number of tests that will fail or reveal faults in the system. So we only want to include those. And to achieve this overarching goal, we began the research by designing a method for test case selection, which attempts to overcome a number of shortcomings in existing test case selection approaches. And we reviewed some of the most popular existing regression testing optimization methods and pinpointed a number of drawbacks. So first, you have methods that use code coverage techniques, in which the coverage of statements or blocks in the system under test is first measured, and then tests are selected based on the total number of statements or blocks that they cover. And in such approaches, the main drawback is that the time they require to write and update code coverage reports in a timely manner to desk might be too large. And then we have techniques such as deja vu, ecstasy, and fault tracers, and all of those techniques, they dynamically compute the set of impacted tests on the old code revision in order to decide which subset of tests should be included in the new revision. And the main drawback in these approaches is their reliance on this dynamic identification. So they need to run the test cases. And for large projects, such information might be very time consuming. And second, not all the time, information about those impacted test cases may not always be available. So that's also another limitation. And then we have approaches that use static-based analysis, such as class SRTS and meth SRTS. And these approaches, they require to parse the code or generate relational graphs. And the main drawback here is that they're programming language specific. They work on specific programming languages. They're computationally expensive, and they also have a tendency of over-approximating the set of impacted test cases. So based on those number of drawbacks or shortcomings, we designed this test case selection method. We adopted the design science research methodology to develop a method for test case selection. And we wanted to answer the question of how can we reduce the number of executed test cases by selecting the most effective set of test cases when integrating new code changes. So when we designed the method, we had these few objectives in mind. First, we wanted the method to work on any programming language. We wanted it to be language agnostic. We want it to be lightweight, so it doesn't require a lot of time, to collect, select, and execute test cases. And we also want it to be modular in a sense that you can plug different algorithms in the pipeline of the method in an easy fashion. So the method that we designed for test case selection was named MeBoTS, which stands for Method Using Bag of Words. And the method is based on a machine learning classifier that learns test case selection by modeling dependency between historical source code changes and their respective test case execution outcomes. And in the first study of my research, we tested the effectiveness of the method on a fine grain level of granularity, which means that we wanted to model dependency between changes made on a statement level and test execution outcomes. And the way the method works can be broken down into 3 steps. In the first step, the method begins by collecting a sample of historical code changes from the development repository of the system being tested, and all the set of test cases that was executed against each of the collected commit. And historical code changes are extracted by, from several pairs of revision by performing a diff operation. So suppose that we want to extract the code changes or the deltas between these 2 revisions, then we perform a diff operation and we get a delta of 1 line of code. Since this was the only modified line in revision 2 relative to revision 1, we then store this modified line in a file, which we refer to as a corpora of code changes. And finally, we look at all the test cases that were executed against revision 2, and we select one test case whose outcome or whose execution outcome changed from revision 1 to revision 2, which means that this test case reacted to the changes made between revision 1 and revision 2. And in this example, we picked a test case that changed from fail to pass, and we use that value to annotate this extracted line of code. And the next step of the method, we transform the lines collected from step 1 into feature vectors using a feature extractor algorithm. And in our method, we use the bag of words approach to make this transformation from text into feature vectors, where each vector corresponds to a token found in the lines of code being analyzed. And the table here shows an example of how the generated feature vectors would look like after being exposed or modeled using the bag of words approach. And finally, in the last step of the method, we use the generated feature vectors to train a machine learning classifier to predict whether new lines of code that appear in future revisions would trigger a test case to fail or to pass. And based on those predictions, we can either, we will take all the tests that the model predicted to pass and exclude those. I would only include tests that were predicted to fail and include them in the build regression suite. And we evaluated the effectiveness of this method using a data set that was collected from historical code changes of a program written in the C language at a software telecommunication company. And the collected data contained 12 test cases, 82 test executions, testing about 1.4 million lines of code. And the evaluation of the tool was done by measuring 2 performance measures, the recall and the precision. With recall, we can measure how many test cases passing will the model or the method identify as passing, while with precision, we can measure how many test cases identified as passing will actually pass. And the main 2 findings that we drew from this study were that first, the size of the code changes extracted between pairs of revision plays an important role in influencing the predictive performance of the model in MeBoTS. So when we used a mix of large and small commits for building the model, we observed some randomness in the prediction with a recall of 31% and a precision of 51%. Whereas when we used a training data set of smaller code commits, we could observe an improvement in the recall reaching to 49% and an increase in precision reaching to 73%. The second finding from this study was that using tree-based model for test case selection provides similar performance or predictive performance as compared to deep learning models. And therefore, we argue that using tree-based model is more appropriate maybe in test case for the context of test case selection, because it has this white box nature and its computational cost is lower compared to deep learning model. Now, despite the improvement that we achieved in the performance of the classifier after using smaller code commits for training, we still considered a recall score of 49% to be relatively low. And for this reason, we manually scrutinized the data we have to identify some suspicious patterns in the data. And what we observed was that a large number of lines in the data were actually duplicate, appearing with different class values. So in this code fragment and its equivalent matrix of feature vectors, you can notice how lines 8 and 13 are duplicate with respect to their feature vectors. Yet those 2 lines are assigned with a different class label. And we refer to such lines as contradictory because different class labels are characterized by the same set of feature vectors. And due to this contradiction in the labeling for the same lines, we say that these lines are noisy with respect to their class. So we had a large number of such contradictory entries in the line, and we speculated that they might be harmful on the performance, the predicted performance of the model in MeBoTS. And we wanted to see, okay, so what does the literature say about this type of noise or about such occurrences of data points in a data set? So we reviewed the literature, and we found that several researchers actually concluded in their work that class noise does have an impeding effects on the classification performance for MeBoTS, and thus it should be handled before building a classifier. However, we did not find any empirical study in the literature that discussed the effects of class noise in the software engineering discipline. And therefore, in the second study of my research, I wanted to study the effects of class noise on the performance of the classifier in the context of test case selection. And for that, we conducted a controlled experiment to answer the question of, is there really a statistical difference in the predictive performance of the model for test case selection in the presence and absence of noise? of class noise. So in our experiments, we used the same data set of code changes presented in the first or described in the first study. And we started the experiments by generating experimental subjects that we wanted to apply the treatment to. And then we seeded 6 different levels of class noise, which is the treatment here, and tested the performance of the classifier using a holdout subject. And after that, we recorded the performance of the model in MeBoTS in terms of precision, recall, F-score, and Matthew correlation coefficient. And finally, we statistically compared the classification performance scores attained by the model when trained under each of the seeded level of noise, class noise, and when trained on data that contained no class noise. And 2 main findings drawn from this experiment. The first was that as the ratio of class noise increased, as we seeded higher ratio of class noise into those experimental subjects, we noticed that the precision of the model dropped, which means that our confidence in the prediction made by the model of those unimpacted test cases also decreased. And the second finding suggests that the model's ability to identify unimpacted test cases gets affected as class noise exceeds 20%. So in the third study of my research, we worked towards improving the predictive performance of the classifier in MeBoTS. And this study had 2 folds. In the first fold, we wanted to design a tool that reduces the effect or reduces the ratio of class noise, since we could conclude that it had a detrimental effect on the prediction. And in the second fold, we wanted to see if handling another type of noise called attribute noise can even further improve the predictive performance of the model. But what is really attribute noise? So a data point is said to be noisy with respect to its attribute when it contains corrupted or irrelevant information. And those corrupted or irrelevant information, those could be empty values, wrong values, or outlier values. And my research, data points whose attributes appear to contain outlier values or exceptional values are treated as noisy with respect to their attributes, because those exceptional values can be harmful to the classifier if they appear coincidentally without adding any meaningful information about faulty patterns in the code. So what we see here, this code fragment and its equivalent feature vectors show that the if statement on line 17 deviate in its attribute values from the attribute values in lines 9 and 13. So we say that line 17 is noisy with respect to its attribute because of this deviation, or it's the exceptional values that appeared in its feature vectors compared to the other if statements. So in the third paper, I wanted to answer the question of, okay, how can we improve the predictive performance of a learner for test selection by handling class and attribute noise? So what is really the best combination? Should we handle both? Should we just handle one of those? Which combination would yield to the best predictive performance? So for the first fold, remember I said that we wanted to design a tool to reduce the ratio of class noise. So we designed a tool for that purpose, and the tool actually fixes the label values in lines that are in contradiction. And if the tool encountered 2 contradictory entries in the data, one which is labeled with 0 and the other is labeled with 1, then it would relabel the class value of the line annotated with 0 to 1. The tool is lightweight in terms of the computational time. It took a few minutes to finish, to handle the noise in the data and in the data set that I worked with. And the effectiveness of this tool was evaluated by applying it to the data described in the first study, and then by comparing the predictive performance of the model in MeBoTS before and after using this tool. And for the second fold of this study, which was to examine the effect of attribute noise on the predictive performance of the model in MeBoTS, we conducted a control experiment using the same data set as well from the first study. And we started the experiments by generating experimental subjects using stratified cross-validation. And then we used an existing algorithm from the literature, which is called PANDA. And the PANDA algorithm helps us identify lines that came with the highest attribute noise values. And then after identifying those lines with attribute noise, we started by removing fractions of those lines from the data. And after removing every fraction of lines, we trained the classifier in MeBoTS and recorded its predictive performance to see if noise removal with an attribute noise removal can actually, improve the performance of the model. So we recorded the 4 performance measures: performance, precision, recall, F score, and matrix correlation coefficient. And finally, we statistically made this comparison between those measures after removing each fraction of attribute noise and with the performance measures on the original data. So our findings showed that reducing class noise only on its own is essential for improving the predictive performance. It actually provided the highest performance scores for the model, whereas the findings suggest that it is counterproductive maybe for testers to bother about removing data points that contain high attribute noise, since no improvement in the predictive performance of the model in MeBoTS could be observed. And in the last study of my research, we wanted to improve the predictive performance of the MeBoTS again, of the model in MeBoTS. So we constructed a taxonomy of dependencies between code changes and different test case types from the viewpoints of tester. And the purpose is to be able to actually construct the training data for MeBoTS based on, valid dependencies between what we map between the code changes and the test case execution outcomes. So by valid, I mean, so there will be some test case types that react upon certain code changes. So we wanted to understand what type of test cases will react to those code changes. And according to our knowledge, there is no existing taxonomies in the literature that make such a classification. The most related taxonomies are, they classify defect types. So in this last study, adopted a design science research methodology to answer the question of to what degree do software testers perceive content of code, commit, and test case types to be dependent. So we used a combination of qualitative and quantitative data collection methods. We started by reviewing papers that empirically discussed the dependencies between different test case types and code changes. And then we distributed a survey to 9 testers at software center companies to get their views about potential dependencies between code change types and test case types. And we extracted all the terms or the categories of code changes and test case types from the first step and from the literature review. And then in the last step, we held a workshop with 6 testers where we discussed together, the strengths of the dependencies, not just what test case depends on what code change, but also like how strong the dependency they perceived. Yeah. And the validation of this taxonomy was done using orthogonality demonstration, which is by discussing the connections between the test case types and the code changes. So the findings from this study showed that memory management changes, for example, lines that contain words like new, delete, or malloc, should be tested with performance, capacity, load, stress, soak, and volume test. Similarly, the second finding suggests that with complexity code changes, for example, changes that contain nested loops, those should be also tested with the same test case types as memory management, in addition to maintainability test. And the final finding was that there was a lack of consensus between testers about the relationship between memory management and complexity code changes on the one hand, and security tests on the other hand. So in terms of the practical implications, first, our research revealed that MeBoTS allows software developers to pinpoint 74% of defective lines that should be further scrutinized before being submitted to the work repository. Second, MeBoTS can assist test orchestrators to remove 81% of tests that were predicted to be unimpacted from the build regression suite. And this doesn't mean that we are encouraging testers not to rerun all available tests before releasing a new software version, but we're just trying to help maximize, the probability of detecting faults in new code changes as they appear, so that developers can fix them as soon as they appear. And finally, MeBoTS can also help, feed software architects and security experts with information about architectural and security flows in the system. So, for example, if MeBoTS could identify lines of code that are related to memory changes, and based on the dependencies that we capture, we know that memory changes might affect certain quality of the system. So we would feed we would pinpoint to a software architect and a security expert those lines that can help them understand better how to overcome these flaws in the system. So finally, closing the presentation with some open-ended questions for future work. The first question is whether the effectiveness of MeBoTS can be improved if we construct training data based on the dependencies that we identify. So I would like to validate the taxonomy by applying it on software artifacts and not just by discussing the orthogonality of the dependencies, and see whether those really, tests that were identified as dependent will actually react to those code changes. And we also want to see if we could build or construct a training data for the model in MeBoTS using such dependencies. Will that improve the predictive performance of the model in MeBoTS? And second, since any test case selection technique, is said to be cost effective based on the time it takes to collect, select, and execute the test, it is also important to compare the time it takes MeBoTS to select test cases with existing approaches. The other question is whether MeBoTS can be used to test flakiness of tests. So, flakiness in tests can be due to several factors, such as issues in the code or issues in the test script, or maybe external factors. And one approach that has been investigated, Software Center, I know about that, is that first they start by selecting tests whose verdicts changed from one outcome to another, and then they would compute the git diff between the pair of revisions, and then they would see if the selected tests do not cover what has been changed between the respective pairs of revisions. And then, if those test cases don't really cover what's been changed, then they label those tests as flaky. So maybe this calls for future collaboration with the team at Software Center working on this flakiness and to test if MeBoTS can be used to help in predicting those flaky tests. And then an open-ended question is whether MeBoTS can be effective in detecting, if MeBoTS can operate on a higher level of abstraction. So will MeBoTS be more effective if we trained it on coarser grained level of code rather than fine grained level? So that's also another open-ended question. And finally, we want to see whether the conclusion drawn about the effect of attribute noise was just coincidental, whether it was just related to the programming language or the domain in which it occurred. We want to examine the impact of attribute noise on test case selection when on different data sets from other programming languages such as Java or Python. And with this, I conclude my presentation, and I thank you all for attending.